Hey guys, welcome to the Science Hub. In this module 7, we are going to study about data acquisition and duplication. So, the module objectives are data acquisition, types of data acquisition systems, data acquisition formats, data acquisition methods, determining the best acquisition method, contingency planning for image acquisitions, static data acquisitions, live data acquisitions, volatile data collection methodology, types of volatile information, disk imaging tools requirements, validating data acquisitions, Linux validation methods, Windows validation methods, acquisition best practices, data acquisition software tools, and data acquisition hardware tools. Data acquisition is the process of imaging or otherwise obtaining information from a digital device and its peripheral equipment and media. Static acquisition. This type of data is termed as non-volatile and is usually recovered from hard drives. It can also exist in slack space, swap files, and unallocated drive space. It is defined as acquiring data that remain unaltered when the system is powered off or shut down. Other sources of non-volatile data include CD, ROMs, USB thumb drives, smartphones, and POAs. Live acquisition. It is defined as acquiring data from a running computer. It is computer that is already powered on when encountered at a crime scene that would be lost when powered off. This type of data is termed volatile and resides in registries, cache, and RAM. As RAM and other volatile data, dynamic collection of this information should occur in real time. Data acquisition format. There are basically three data acquisition formats. That is, first, raw format. To preserve the digital evidence, vendor and some OS utilities are allowed to write bitstream data to files. This copy technique creates simple sequential files of a dataset or suspect drive. The output of these flat files is referred to as a raw format. Advantages and disadvantages. That is, first, fast data transfer. Disadvantage: requires as much storage as original disk or dataset. Can ignore minor data read errors on source drive. Most computer forensic tools can read raw format. There are disadvantages. Tools, mostly freeware versions, might not collect marginal sectors on the source drive. Freeware tools have a low threshold of retry reads on weak media spots on a drive, whereas commercial acquisition tools have a higher threshold to make sure all data is collected. Second, proprietary format. Commercial forensic tools have their own formats to collect the digital evidence. Proprietary formats usually offers features that counterpart the vendor's analysis tools, such as option to compress or not compress image files of a source drive to save space on the target drive, ability to split an image into smaller segmented files to archive such as CD or DVDs with the data integrity checks integrated into each segment, ability to integrate metadata into the image file such as date and time of acquisition, hash value of the suspect drive, investigator name, comments, case details, etc. Disadvantages include inability to charge an image between different computer forensic analysis tools. That are examples: Hook Investigator Z-Imager produces three proprietary formats, namely IDIF, IRBF, and IEIF, that can be read only by Hook. Files has limitation for each segmented volume. Third, Advanced Forensic Format. Advanced Forensics format is an open source acquisition format with the following design goals. File extension includes .afm for AFF metadata and .afd for segmented file image files. No site restriction for disk to image files. Generate compressed or uncompressed image files. Provide space for the metadata and the rich image file or segmented files. Simple design with extensibility. Open source for multiple computing platforms and OSs. Deal integrity consistency check for the self-authentication. Bitstream vs backups. Bitstream, that is mirror image or evidence grade backups, involves capturing data on the copied media. This includes hidden and residual data, that is slack space, swap, unused space, residue, deleted files, etc. Bitstream programs rely upon CRC computations in the validation processes. Most operating systems pay attention only to the live tile system structure. Slack, residue, deleted, etc. are not indexed. Backups usually do not capture this data and they modify the timestamps of data, contaminating the timeline. Now, why to create a duplicate image? The computer, that is media, is a crime scene and it should be protected to ensure that the evidence is not contaminated. Duplicate image allows the following: preserve the original evidence, prevents inadvertent alterations of original evidence during examination, allows recreation of the duplication image if necessary. Evidence can be duplicated with no degradation from copy to copy. The issue with data duplication. Data duplication may contaminate the original data, which would then not be accepted as evidence. There are chances of tampering with the duplicate data. Data fragments can be overwritten and data stored in the Windows swap file can be altered and destroyed. If the original data is contaminated, then important evidence is lost, which causes problem in the investigation process. Now, data acquisition methods. It is first bitstream, that disk to image file. It is the most common method used by all forensic investigators. With this method, one or many copies of the suspect drive can be generated. The copies are bit or bit replication of the original drive. Tools such as ProDiscover, EnCase, FTK, the Sleuth Kit, X-Ray Forensics, iLook Investigator, etc. can be used to read the most common type of disk to image files generated. Bitstream disk to disk. Because of software or hardware errors or incompatibilities, it is sometimes not possible to create a bitstream disk to image file. To solve this problem, create a disk to disk bitstream copy of the suspect drive using tools such as EnCase, CFBack, and Norton Ghost. These programs can alter the target disk geometry, its head, cylinder, and track configuration such that the copied data matches to the original suspect. Data acquisition mistakes. An investigator may commit some common mistakes while collecting data from the system that result in the loss of critical evidence. Common mistakes committed by investigators include choosing wrong resolution for data acquisition, use of wrong cables and cabling techniques, insufficient time for system development, making the wrong connections, poor knowledge of the instrument. Rules of thumb. Produce 2 copies of the original media, that is, one copy is the working copy to be used for analysis, one copy is the library control copy that is stored for one circle E purposes or in the event that the working copy gets corrupted. If performing drive to drive imaging, use clean media to copy the shrink wrapped new driver. Once duplication of original media is done, verify the integrity of copies to the original. Static data acquisition. Static data is that remains unchanged after shutting down the computer and is found on hard drives and removable storage media such as USB drives, flash cards, CD-ROMs, and other external hard drives. Examples of static data are emails, word processing, documents, web activity, spreadsheets, select space, swap files, unallocated drive space, and various deleted files. Static data that can be recovered from a hard drive includes temporary files, system registries, event system logs, boot sectors, web browser cache, cookies, and hidden files. Live data acquisition. Computer uses random access memory RAM to write the current processes it is using as a form of virtual clipboard. This data is volatile because it goes away and is irretrievable when the system is shut down or rebooted. Volatile data resides in registries, cache, or RAM that is the most significant source of data acquisition. Potential evidence may be lost or destroyed by simply looking through files on a running computer or by booting up the computer to look around or play games on it. In volatile data collection, contamination is harder to control because tools and commands may change file access data, dates, and times, use rare files, libraries, or DLLs, trigger the execution of malicious software, malware, or worst case, force a reboot and lose all volatile data. Why volatile data is important? Volatile data is important as it contains useful information to the investigator. For example, running processes, passwords and clear text, instant messages, executed console commands, internet protocol addresses, Trojan horses, unencrypted data. Additional useful volatile data includes who is logged into the system, open ports and listening applications, registry informations, system informations, and attached devices. Common mistakes in volatile data collection. Assuming that some parts of the suspicious machine may be reliable and usable, using native commands on the suspicious computer may trigger time bombs, malware, and Trojan to delete key volatile data. Shutting down or rebooting the suspicious computer's connection and running processes are closed and the MAC time are changed. Not having access to baseline documentation about the suspicious computers. Not documenting the data collection process. Volatile data collection methodology. First, incident response preparation. Second, incidents profile creation. Third, policy verification. Fourth, volatile data collection strategy. Fifth, volatile data collection setup. And sixth, volatile data collection process. Disk imaging tool requirements. Based on the disk imaging tool, requirements are divided into two categories: mandatory requirements and optional requirements. All the disk imaging tools must accomplish the task described as mandatory requirements. The tools may or may not provide the feature discussed under the optional requirement. Disk imaging tool requirements, that is mandatory. The tool should not change the original content. The tool should log I/O errors in an accessible and readable form, including the type and location of the error. The tool must have the ability to be held up to the scientific and peer review. Results must be repeatable and verifiable by a third party if necessary. The tool should alert the user if the source is larger than the destination. Data acquisition. Digital evidence validation involves using a hashing algorithm utility to create a binary or hexadecimal number that represents the liquefies of a data set such as disk drive or file. The unique number is referred to as a digital fingerprint. Hash values are unique if two files have the same hash value. They are 100% identical even if the files are named differently. Utility algorithms that produce hash values include CRC32, MOS HSA1, and SHA312. CRC32. It is a 32-bit cyclic redundancy check code used as an error detection method using data transmission. If the computed CRC bits are identical to the original CRC bits, it means that no error occurred. MD5. It is a cryptographic hash function with a 128-bit hash value. The hash value can be used to demonstrate integrity of data and can be performed on various data types such as files, physical drives, partitions, etc. SHA1. It is cryptographic hash functions that produce a message digest that is 160 bits long. Remote data acquisitions. Data can be copied from a suspect computer by connecting remotely to it via network connection. Remote acquisitions tools vary in configuration and capabilities. Some require manual intervention on remote suspect compute to initiate the data copy. Some acquire data covertly through an encrypted link by pushing a remote access program to the suspect's computer. Remote acquisition should be done as a live acquisitions, not as a static acquisitions. Drawbacks. Lens data transfer speeds and routing table conflicts could cause problems. On a WAN, problem in gaining the permission needed to access mere secure subnets. Heavy traffic on the network could cause delays and errors during the acquisition. Remote access program being detected by the anti-spyware, antivirus and firewall tools. Remote acquisition can be performed using remote acquisition tools such as ProDiscover, Whetstone Liveware, F-Response, runtime software that is Disk Explorer for FAT, Disk Explorer for NTFS, and HD Host. Acquisitions best practices: permit only authorized personnel to access. Maintain list of individuals involved in the search. Note when the system was last accessed. Establish a chronology of access to the media. Do not turn the system on, off, it is or. Place all the magnetic media in anti-static packages. Properly label the containers used to hold evidence. Protect the evidence from extremes in temperature. DD command. These are the DD command syntax. Suppose a 268 hard disk is seized as evidence. Use OD to make a complete by-scale backup of the hard disk. Copy one hard disk partition to another hard disk. Make an ISO image of a CD. Restore a disk partition from an image file. Copy RAM memory to a file. dcfldd command works similar to the DD command but possesses many features designed for computer forensics acquisitions. Following are the important functions offers that are possible with DD. Hashing on the fly. dcfldd can hash the input data as it is being transferred, helping to ensure data integrity. Status output can update the user as if its progress in terms of the amount of data transferred and how much longer operation will take. Flexible disk wipes can be used to wipe task quickly and with a known pattern it's desired. Image wipe can verify that a target drive is a bit for bit match of the specified input file or pattern. Data from a 64 MB USB drive runs the command from a privileged root shell session. Type up the following command at the shell prompt to acquire an entire media device in one image. Multiple outputs can output to multiple or disk at the same time. Split out can split out to multiple files with more configurability than the split command. Piped outputs and logs can send all its kg data and output to commands as well as files natively. If the disk or suspect media is to be segmented, use the dcfldd command with the split command, placing split before the output file field as shown below. Extracting the MBR. To see the contents of MBR, use the command ddif equals /dev/had of equals mbr.bin, bs equals f512, count equals 1, od xambr.bin. The dd command, which needs to be run from root, reads the first 512 bytes from /dev/had, the first integrated drive electronics or IDE drive, and write them to the mbr.bin files. The od command prints the binary file in hex and ASCII formats. Tool FTK. Forensic Toolkit FTK is recognized around the world as a standard in computer forensic investigation technology. The court-validated platform delivers cutting-edge analysis, decryption, and password cracking, all within an intuitive, customizable, and user-friendly interface. In addition, with FTK, you have the option of utilizing a back-end database to handle large datasets, or you can work without one or application. Simplicity is your goal. Representative image is the image about FTK, Forensic Toolkit. Features of FTK: perform network-based secure single system forensic acquisition of physical devices, logical volumes and RAM. File type and file system identification and enumeration. Embedded Oracle database and powerful index search engine. Create images, analyze the registry, conduct an investigation, decrypt files, crack passwords, identify test steganography, and build a report. Recover passwords from 100 plus applications, harness ideal CPUs across the network to decrypt files and perform robust dictionary attacks. Representative image is describing about the working of FTK. Tool EnCase Forensic. EnCase Forensic is a powerful investigation platform that collects digital data, performs analysis, reports on findings and preserves them in a code-validated, forensically sound format. Features of EnCase Forensic: produces an exact binary duplicate of the original drive or media, verifies duplicate copies by generating MD5 hash value for related image file, acquires data from disk or RAM, documents image, email, webmail, internet artifacts, web history, etc. View hundreds of file formats in a native form, built-in registry viewer and integrated photo viewer, recover file and partitions, detects deleted files by parsing, event logs, file signatures analysis and hash analysis. Representative image is describing about the working of EnCase Forensic. Tool MASSter Solo 4 Suffocate. It is a forensic hard drive duplicator that offers investigator the ability to image one suspect drive to two evidence drives or two separate suspect drives to individual evidence copies one simultaneously at SATA 2 speed. It authenticates with SHA1, SHA2, MD5 and also supports ID5, RAID, SATA drives as well as a variety of micromedia cards. It also offers a bulk-in Gigabit Ethernet connection, allowing the investigator to upload image to storage area network for the purpose of processing and archiving images. Tool MASSter Roadmaster 3. The Roadmaster 3 forensic data acquisition and analysis tools is designed to perform both as a fast and reliable hard drive imaging and data analysis unit. It is an advanced computer forensic tool used by law enforcement agencies as well as corporate security to acquire and analyze data. It can image hard drives of any kind as well as capture data from other media and unopened computer and support different copy formats and hashing methods. Tool TDI Forensic Duplicator. TDI Forensic Duplicator provides disk to file or disk to disk duplication for the following setups, that is IDE to IDE, IDE to SATA, SATA to SATA and SATA to IDE. It is a disk drive wiper with disk blank check, display log disk information, hash disk verification hash, the ability to generate and save duplication logs and device and duplication process setup. It recognizes and automatically defects HPA and prompts the user for DC or defect action. Thank you guys. Please visit www.thescihub.in for further updates.